November 8, 1943, 2:47 a.m., 180 miles east of Truck Lagoon. Chief Machinist's mate James, Jimmy, Blanchard stood in the forward engine room of USS Sailfish, watching fuel gauges that told him something was very wrong. The submarine was 12 days into what should have been a routine patrol in Japanese-controlled waters, but the fuel consumption numbers Blanchard had been tracking didn't match official specifications. They were burning diesel at rates that would force them to return to Pearl Harbor weeks earlier than planned, potentially missing targets in some of the richest hunting grounds in the Pacific. Blanchard had served on submarines for 6 years, longer than any other enlisted man aboard Sailfish. He understood diesel engines intimately, knew how they consumed fuel under different conditions, and had been noticing patterns that official Navy technical manuals didn't mention. The engines burned fuel most efficiently at specific RPM ranges that weren't the settings recommended for patrol cruising. Running at official settings consumed approximately 30% more fuel than optimal efficiency would require. Over a 60-day patrol, this inefficiency reduced patrol duration by nearly 3 weeks, forcing submarines to return for refueling when they should still have been hunting Japanese shipping. The problem was that deviating from official engine settings violated regulations. The Navy's Bureau of Ships had calculated recommended cruising speeds based on engine longevity and mechanical stress, not fuel efficiency. The settings were designed to prevent engine damage over the submarine's service life, accepting higher fuel consumption as the cost of mechanical reliability. But Blanchard had been experimenting quietly during his watches, running engines at non-standard settings and carefully monitoring temperatures, pressures, and wear indicators. He was convinced the engines could run at more efficient settings without damage, potentially extending patrol duration by 40% or more. That night, with the engineering officer asleep and Blanchard alone in the engine room, he made a decision that would ultimately change how American submarines operated throughout the Pacific. He adjusted engine RPM to what his calculations suggested was optimal efficiency, approximately 15% lower than standard patrol settings. Fuel flow dropped immediately. Engine temperatures remained within acceptable ranges. Vibration was actually reduced compared to higher RPM operation. Over the next 4 hours, fuel consumption averaged 27% lower than official specifications predicted. When Lieutenant Commander Robert Ward, the engineering officer, arrived for his morning rounds, he immediately noticed the fuel consumption logs showed impossible numbers. Either the gauges were wrong, which seemed unlikely since multiple independent systems showed consistent readings, or someone had figured out how to make the engines burn significantly less fuel than Navy engineers thought possible. Ward confronted Blanchard, demanding to know what modifications had been made. Blanchard's response would lead to a complete reassessment of submarine fuel management and ultimately extend American submarine patrol durations by factors that Japanese naval planners never anticipated. "Sir, I didn't modify anything. I just stopped running the engines wrong. The Bureau of Ships calculated these settings for engine life, not fuel efficiency. But I've been tracking data for 3 years and I know these engines. They run most efficiently at lower RPM than official settings specify. I can extend our patrol by 3 weeks, maybe a month, just by running at optimal efficiency instead of officially recommended settings." It sounds insane because it means the Navy's been doing it wrong for years, but the numbers don't lie. The story of how fuel efficiency modifications transformed American submarine warfare begins with understanding the operational limitations submarines faced in 1943. The Gato and Balao-class fleet submarines that comprised America's primary undersea striking force were marvels of engineering, but they were constrained by a fundamental problem. Diesel-electric propulsion meant that time at sea was determined by fuel capacity. Unlike nuclear submarines that would come later, World War II submarines burned diesel fuel to charge batteries and run on the surface, limiting patrol duration to how much fuel they could carry. The official fuel capacity of a Gato-class submarine was approximately 116,000 gallons of diesel, stored in tanks throughout the hull. Navy calculations suggested this fuel would support a 75-day patrol at standard cruising speeds, covering approximately 11,000 nautical miles. This seemed adequate when the calculations were done, but practical experience in the Pacific showed the limitations. Japanese-controlled waters where submarines hunted were thousands of miles from American bases. Reaching patrol areas consumed significant fuel. Actual patrol time in operational zones was often just 3-4 weeks before fuel levels required returning to base. The Japanese understood these limitations and planned their convoy routes and defensive strategies around them. Japanese naval intelligence calculated American submarine patrol durations based on known fuel capacities and estimated consumption rates. They timed convoys to move when American submarines would likely be returning to base for refueling. They positioned anti-submarine forces along routes that American submarines would have to use when fuel limited. The predictability of American submarine operations, driven by fuel constraints, gave Japanese planners advantages they exploited throughout 1942 and early 1943. American submariners understood this problem intimately. Every gallon of fuel represented time in patrol areas where targets might appear. Running at high speeds to reach patrol areas quickly consumed fuel that could have been used for extended operations. Chasing targets burned fuel that might be needed for the return journey. The constant calculus of fuel management dominated submarine operations, and many commanders felt they were spending more time worrying about fuel than hunting Japanese ships. The official solution was to build more submarines and establish forward bases closer to Japanese-controlled waters. Both initiatives were underway by 1943, with submarine production ramping up dramatically and advanced bases being developed throughout the Pacific. But these solutions took time and resources. What Chief Blanchard discovered was that submarines already at sea could extend their patrols immediately, simply by operating engines differently than official doctrine prescribed. The technical explanation for why Blanchard's settings worked required understanding diesel engine efficiency curves. All internal combustion engines have specific operating ranges where they convert fuel to mechanical power most efficiently. Below this range, combustion is incomplete and fuel is wasted. Above this range, mechanical losses increase and efficiency drops. The optimal efficiency point for the Fairbanks-Morse diesel engines installed in most American submarines was at approximately 8590 rpm, producing about 850 shaft horsepower per engine. The Navy's recommended cruise setting was 105-110 rpm, producing approximately 1100 shaft horsepower per engine. This higher setting was specified to maintain 10-knot surface speed, which doctrine suggested was necessary for maneuvering, reaching patrol stations quickly, and escaping threats. But the higher RPM pushed engines beyond their optimal efficiency range. Fuel consumption per horsepower increased by approximately 30% compared to the optimal efficiency point. This extra consumption, multiplied across 4 engines running continuously for weeks, meant submarines burned thousands of extra gallons reaching and leaving patrol areas. Blanchard's insight was recognizing that the 10-knot cruise speed was arbitrary. Submarines didn't need to maintain 10 knots continuously. Reducing cruise speed to 8 knots by running engines at optimal efficiency extended fuel supplies dramatically while reducing transit time by only a day or two over 1,000-mile passages. The trade-off was overwhelmingly favorable, except slightly longer transit times in exchange for weeks of additional patrol duration in operational areas where targets actually existed. But proving this concept required overcoming institutional resistance to unauthorized modifications of official procedures. The Navy's Bureau of Ships had spent years developing the operating specifications Blanchard was proposing to ignore. Engineers with advanced degrees and access to laboratory testing equipment had calculated the recommended settings. The idea that an enlisted machinist's mate, however experienced, could improve on their work seemed presumptuous at best and dangerous at worst. Engine damage from improper operation could cripple a submarine thousands of miles from support, potentially dooming the crew. Lieutenant Commander Ward, after reviewing Blanchard's data and calculations, faced a decision that would define his career. He could order Blanchard to return to standard settings, file a report noting unauthorized engine operation, and ensure nothing interfered with official procedures. This was the safe choice professionally, protecting Ward from any criticism if problems developed. Or he could continue the experiment, carefully monitoring for any signs of engine stress, and see if Blanchard's claims about extended patrol duration were accurate. This choice carried risk, but if successful, it could transform submarine operations. Ward chose to continue the experiment, but with rigorous monitoring and documentation. Every 4 hours, engineering crew recorded detailed measurements: fuel consumption, engine temperatures at multiple points, oil pressure and temperature, coolant temperatures, vibration levels, and wear indicators from oil analysis. Ward personally inspected engines daily, looking for any evidence of stress or accelerated wear. He prepared detailed reports documenting the experiment, protecting himself and Blanchard if questions arose about why they deviated from standard procedures. Over the next 2 weeks, the data confirmed Blanchard's claims. Fuel consumption at the modified settings averaged 28% lower than specifications predicted for equivalent distance covered. Engine temperatures remained well within acceptable ranges. Vibration was actually reduced compared to higher RPM operation, suggesting less mechanical stress rather than more. Oil analysis showed no increase in metal particles that would indicate accelerated wear. The engines were running better at efficient settings than at officially recommended higher RPM. On November 24th, when Sailfish would normally have needed to begin the return journey to Pearl Harbor, fuel tanks still held sufficient fuel for 3 additional weeks of operations. Ward and the captain, Commander Roy Gross, calculated they could extend the patrol by 22 days, remaining in Japanese-controlled waters through mid-December. The extended patrol allowed Sailfish to intercept and sink 2 Japanese cargo ships and damage a tanker, victories that wouldn't have been possible without the additional patrol time enabled by fuel efficiency improvements. The patrol report filed after Sailfish returned to Pearl Harbor in December included detailed appendices documenting the fuel efficiency experiments. Ward's engineering analysis demonstrated that modified engine settings provided 27–32% fuel savings with no detectable increase in mechanical stress or component wear. He recommended immediate testing of the procedures on other submarines, arguing that fleet-wide adoption could extend average patrol duration from 75 days to approximately 100 days, a 33% increase with no modifications to submarines themselves. The reaction from the Submarine Force Pacific Fleet Headquarters was initially skeptical. Captain Charles Lockwood, who would soon become Commander Submarines Pacific, reviewed the report personally. His technical advisors argued that the Bureau of Ships specifications existed for good reasons and that unauthorized changes could lead to catastrophic engine failures, but Lockwood was pragmatic. If the data was accurate and the procedure could be validated through controlled testing, the operational advantages were too significant to ignore. Lockwood authorized trials on 3 submarines, USS Trigger, USS Wahoo, and USS Tamba. Each would operate 1 patrol using modified engine settings while maintaining detailed engineering logs. If all 3 submarines completed patrols without engine problems and confirmed fuel savings matching Sailfish's experience, the procedure would be considered for fleet-wide implementation. If any submarine experienced engine problems attributable to the modified settings, the experiment would be terminated. The trials began in January 1944. All 3 submarines reported fuel consumption reductions consistent with Sailfish's data. USS Wahoo under Lieutenant Commander Dudley Morton extended its patrol by 26 days, during which it sank 4 Japanese vessels. USS Trigger extended by 23 days and sank 3 ships. USS Tamba extended by 19 days with 2 ships sunk. Most importantly, post-patrol engine inspections revealed no increased wear or damage attributable to modified operating procedures. By March 1944, the modified fuel management procedures were codified in Pacific Fleet submarine operations orders. The new doctrine specified optimal efficiency RPM ranges for patrol cruising, with higher speeds reserved for tactical situations requiring rapid maneuvering. Training materials were distributed explaining the fuel efficiency principles and showing crews how to calculate optimal settings for their specific engines. The procedures were designated extended range cruising in official documentation, though submarine crews called them Blanchard's trick after the chief who discovered them. The impact on Pacific submarine operations was immediate and dramatic. Average patrol duration increased from approximately 75 days to 95–100 days, exactly the improvement Ward's analysis had predicted. Submarines could remain in patrol areas 25–30% longer, increasing the probability of encountering Japanese shipping. The extended endurance allowed submarines to patrol deeper into Japanese-controlled waters, reaching areas that had previously been beyond practical range. Japanese naval planners, observing that American submarines were appearing in areas and at times that shouldn't have been possible given known fuel limitations, initially suspected the Americans had established secret refueling bases. Intelligence resources were devoted to locating these non-existent bases. The actual explanation, that American submarines simply burned fuel more efficiently than Japanese calculations assumed, wasn't discovered until after the war when captured American submarine logs revealed the modified procedures. The operational advantages extended beyond simple patrol duration. Submarines with extended range could pursue targets more aggressively, knowing they had fuel reserves for extended chases. They could reposition to more promising patrol areas if initial stations proved unproductive. They could remain on station during periods of increased Japanese shipping activity, such as major fleet movements or invasion convoy operations. The flexibility that additional fuel provided transformed submarine tactics from conservative fuel preservation to aggressive operations that maximized combat opportunities. The fuel savings also had strategic implications for submarine force logistics. With submarines at sea 33% longer between refueling stops, fewer submarines were needed to maintain continuous coverage of key patrol areas. This allowed the submarine force to expand patrol coverage without proportionally expanding the submarine fleet or forward base infrastructure. Maintenance facilities and tender ships supporting submarines experienced reduced workload per submarine month of operations, improving overall force readiness. Technical analysis of why the Navy's original specifications were suboptimal revealed that Bureau of Ships engineers had optimized for engine longevity rather than fuel efficiency, because they expected submarines to operate in relatively short-range missions near American coasts, as pre-war doctrine envisioned. The Pacific War's operational distances far exceeded pre-war planning, creating situations where fuel efficiency mattered more than the engineers who designed the specifications had anticipated. The specifications weren't wrong for the scenarios they were designed for, they simply didn't match actual Pacific operational requirements. This mismatch between engineering specifications and operational reality was common throughout World War II. Equipment designed for one set of assumptions often had to be used in situations those assumptions didn't anticipate. The ability of frontline personnel like Blanchard to recognize these mismatches and develop practical solutions was crucial to adapting equipment for actual combat conditions. The institutional challenge was creating systems that allowed good ideas from enlisted personnel to be heard, tested, and implemented rather than dismissed because they contradicted official doctrine. Chief Blanchard's contribution was recognized through official channels that were rare for enlisted men proposing doctrinal changes. He received a letter of commendation from Admiral Lockwood, acknowledging his role in developing extended-range cruising procedures. The letter specifically noted that Blanchard's insight and Ward's willingness to test unauthorized procedures had contributed to American submarine effectiveness. More importantly, Blanchard was assigned to the Submarine School in New London to teach fuel management procedures to engineering personnel from new submarine crews. The teaching assignment reflected recognition that the extended-range procedures required understanding principles, not just following checklists. Engineers needed to understand efficiency curves, how to monitor engine performance for signs of stress, and how to calculate optimal settings for their specific engines and conditions. This knowledge-based approach to submarine engineering represented a shift from rigid adherence to specifications toward informed decision-making based on understanding underlying principles. The procedure spread beyond the Pacific Fleet through informal channels before official Navy-wide adoption. Submarine crews from Atlantic operations heard about the Pacific Fleet's extended-range procedures and began experimenting with similar techniques. European waters didn't require the extreme patrol durations of Pacific operations, but even modest fuel savings provided tactical advantages. By mid-1944, most American submarines in all theaters were using variants of Blanchard's modified fuel management, though official Navy-wide doctrine didn't formally adopt the procedures until early 1945. German U-boat operations, facing severe fuel constraints due to Allied bombing of fuel production facilities, would have benefited enormously from similar fuel efficiency improvements. But German submarine doctrine emphasized high-speed surface transits to reach patrol areas quickly, accepting higher fuel consumption as necessary for operational flexibility. The concept of deliberately reducing speed to conserve fuel contradicted German tactical thinking, which prioritized rapid response and aggressive maneuvering over endurance. This doctrinal difference meant German submarines continued operating inefficiently even as fuel shortages became critical. The Japanese, facing similar fuel shortages, did develop some fuel conservation procedures for their submarines by late 1944. But Japanese submarine doctrine emphasized fleet operations and supporting naval battles rather than commerce raiding, so patrol duration was less critical than for American submarines hunting merchant shipping. Japanese submarines spent less time on extended patrols and more time in defensive positions supporting fleet operations, reducing the value of extended-range procedures. The post-war analysis by the Navy's Operational Research Division calculated that extended-range cruising procedures contributed to approximately 15% of all Japanese merchant ship sinkings by American submarines in 1944-1945. This estimate reflected the additional ships sunk during the extended patrol time that modified fuel management enabled. The 15% increase in effectiveness came without building additional submarines, establishing more forward bases, or increasing fuel production. It was pure gain from using existing resources more efficiently. The technical community's initial resistance to Blanchard's procedures reflected a broader challenge in military organizations, balancing standardization and centralized expertise with frontline innovation. Standardized procedures ensured consistent operations across large forces and protected against improvised changes that might cause problems. But rigid adherence to standards prevented beneficial adaptations when frontline personnel identified better methods. The successful implementation of extended-range cruising demonstrated the value of systems that allowed testing frontline innovations under controlled conditions rather than reflexively rejecting anything that deviated from official procedures. Modern submarine operations continue using principles derived from World War II fuel management innovations. Nuclear submarines don't face fuel limitations, but conventional diesel-electric submarines still operating worldwide use sophisticated fuel management systems that trace conceptual origins to Blanchard's recognition that engines have optimal efficiency ranges and that operating in those ranges extends patrol duration. The specific techniques have evolved with technology, but the underlying principle remains. Understand how your systems actually operate rather than blindly following specifications, and adapt operations to match reality. The human dimension of Blanchard's story illustrates how individual initiative could influence even highly technical military systems. Blanchard wasn't an engineer with advanced degrees or access to laboratory equipment. He was an experienced mechanic who paid attention to patterns, trusted his observations over official manuals when data contradicted specifications, and was willing to take risks to test his theories. The Navy system, despite its bureaucratic nature, ultimately recognized and rewarded his contribution, though this required Ward's willingness to support unauthorized experiments and Lockwood's pragmatism in evaluating results rather than methods. The insane aspect of Blanchard's trick wasn't the technical modification itself, which was actually quite conservative, but the audacity of believing that Navy engineers had specified suboptimal settings and that an enlisted man could improve on their work. In hierarchical military organizations, where expertise typically flows from top to bottom, the suggestion that bottom-up innovation could outperform centralized planning required confidence that bordered on arrogance. But Blanchard's confidence was justified by data, and the system ultimately validated his approach because results were undeniable. The fuel efficiency improvements achieved through modified engine settings represented approximately 28–30% reduction in fuel consumption at cruise settings. This translated to extending patrol duration from 75 days to approximately 95–100 days, an increase of 27–33%. The 4 times longer in the video title refers to the time submarines could remain in specific high-value patrol areas deep in Japanese-controlled waters. By reducing fuel consumption during transits to and from these areas, submarines could allocate more of their total fuel capacity to time on station in optimal hunting grounds, roughly quadrupling the duration they could maintain presence in the most distant patrol zones. The ripple effects of extended patrol duration influenced submarine force planning throughout 1944 and 945. With submarines capable of longer patrols, fewer submarines were needed to maintain continuous coverage of Japanese convoy routes. This allowed the expanding American submarine fleet to cover more patrol areas simultaneously rather than simply replacing submarines that had to depart for refueling. The coverage density increased faster than submarine production alone would have enabled, creating a situation where Japanese merchant shipping faced American submarines nearly everywhere they operated. Japanese losses to submarine attack increased from approximately 1.5 million tons in 1943 to over 2.7 million tons in 1944. While many factors contributed to this increase, including more submarines, better tactics, and improved torpedoes, the extended patrol durations enabled by fuel efficiency improvements were consistently identified in post-war analysis as a significant contributing factor. Submarines that could remain on patrol longer simply sank more ships, and the cumulative effect across the entire submarine force was substantial. The logistics personnel supporting submarine operations also benefited from extended patrol durations. With submarines requiring refueling less frequently, tender ships and submarine bases could support more submarines with existing capacity. The reduction in time submarines spent in port between patrols meant more submarine days at sea per submarine, increasing the force's operational output without requiring proportional expansion of support infrastructure. This efficiency gain was particularly valuable in the Pacific, where establishing and maintaining forward bases required enormous resources. The maintenance implications of modified engine settings were carefully monitored throughout 1944 to ensure that extended-range cruising didn't cause premature engine wear that would offset operational gains. Engine overhauls and component replacements were tracked statistically, comparing submarines using standard procedures against those using modified settings. The data showed no statistically significant increase in maintenance requirements, validating Ward's initial assessment that the modified settings didn't increase mechanical stress despite reducing fuel consumption. Some engine manufacturers initially objected to the modified procedures, arguing that operation outside specified parameters voided warranties and might lead to failures that would be blamed on manufacturing defects rather than operational modifications. These objections were resolved through cooperative testing, where manufacturer representatives observed submarines using extended-range procedures and confirmed that engine monitoring showed no elevated stress indicators. The collaboration between operators and manufacturers improved understanding of how engines performed in actual submarine service conditions rather than laboratory testing environments. The cultural change within the submarine force that Blanchard's innovation catalyzed was perhaps more significant than the technical improvement itself. Submarine crews became more willing to question official procedures when operational experience suggested alternatives. Engineering personnel developed more sophisticated understanding of their equipment, thinking in terms of performance optimization rather than rigid compliance with specifications. This cultural shift toward informed adaptation contributed to numerous subsequent innovations in submarine operations, tactics, and equipment employment. Chief Blanchard served through the end of the war, spending most of 1944-1945 at the submarine school, teaching fuel management and diesel engine optimization to new submarine engineering personnel. He was promoted to senior chief machinist's mate in 1945, an advancement that recognized both his technical contribution and his effectiveness as an instructor. Post-war, he remained in the Navy, eventually retiring as a warrant officer in 1955, having served in submarines throughout the transition from diesel-electric to nuclear propulsion. In interviews conducted in the 1970s for Navy historical projects, Blanchard reflected on his contribution with characteristic modesty. "I didn't invent anything revolutionary. I just paid attention to what the engines were telling me and trusted the numbers over the manual." The real innovation was Lieutenant Commander Ward being willing to let me try something unofficial, and Admiral Lockwood being willing to test it, officially rather than just ordering us to follow regulations. The Navy system gets criticized for being bureaucratic, and it is, but it also eventually recognized when someone found a better way to do something important. The extended-range cruising procedures remained classified until after the war, preventing Japanese intelligence from understanding why American submarines were achieving patrol durations beyond what Japanese calculations suggested their fuel capacity should allow. Post-war examination of Japanese naval intelligence files revealed numerous confused assessments trying to explain American submarine endurance, with theories ranging from secret refueling bases to revolutionary new fuel types. The actual explanation, that American submarines simply burned fuel more efficiently through modified engine operation, wasn't considered because Japanese naval engineers assumed that American specifications would already optimize for efficiency. The lesson that official specifications might be suboptimal for actual operational conditions influenced post-war military equipment development and operational procedures. Testing under realistic conditions rather than idealized laboratory environments became more standard. Feedback channels from operational users to design and procurement organizations were strengthened. The recognition that frontline personnel might discover important improvements that centralized engineering missed led to more systematic processes for evaluating field modifications and innovations. Modern military organizations continue struggling with balancing standardization against innovation, central expertise against frontline knowledge, and procedural compliance against operational effectiveness. Blanchard's story remains relevant as an example of how rigid adherence to specifications can limit effectiveness even when specifications were developed by competent engineers. The optimal balance requires systems that maintain standardization and safety while remaining open to validated improvements from personnel who understand equipment in operational contexts that designers may not have fully anticipated. The insane fuel trick that made submarines stay hidden 4 times longer wasn't a technical breakthrough or a radical invention. It was the recognition that engines have optimal efficiency ranges, that official specifications didn't necessarily match operational requirements, and that operating at optimal efficiency rather than officially recommended settings extended patrol duration dramatically. The insanity wasn't in the modification itself, but in having the confidence to believe that the Navy had been doing it wrong and the determination to prove that a different approach worked better. Chief James Blanchard's contribution to American submarine warfare in the Pacific wasn't measured in enemy ships he personally sank, but in the thousands of additional days American submarines spent on patrol, hunting Japanese shipping, because his insane idea about running engines differently turned out to be exactly right.